Hello everybody, and welcome to this series of lectures on computer architecture. Today we're going to take another look at the Finite State Machine. As promised, we're going to take a look at the Mealy Machine, and namely in this case a little bit more complicated example, namely an edge detector. Remember, a Mealy Machine is a full Finite State Machine with input, output and memory. So let's take a look. Let's start with first step that you always have to do is read carefully what it is that we're going to build. That is, let me show it here. What do we want? We want a finite state machine that's called edge detector, that we get a string of input values that I have here, input bits. It's just a string of bits. We have to imagine that it comes in here low voltage, high voltage, and so on. And then we want that the output, we want that it gives an output of 0 if the new bit is the same as the last one, and an output of 1 if there was a change between bits. So you can see, for instance, these here, it goes from 0 to 1. So therefore we want to output a 1, but then it stays 1 here. So we want to output a 0. Now it changes from 1 to 0, so we want to output a 1. And then it stays from 0 to 0, so we output a 0. And we start with the state, the output as 0, as just to have a starting defined state and a starting defined output, and not random. So we want something inside, we want to design what is here inside this black box, or yellow box in this case. What is in this box? We have input, we have output, and now we're going to design what is inside. And the input and output have to follow this scheme which is here, and it's called an edge detector. Okay, so let's start. As we remember, the first thing we have to do when we design a finite state machine is actually to draw the state diagram. And the state diagram is to find out what are all the possible states are, and then see how they are connected to each other. With what input are they going to go from what state to what state? So the first step is to design what states we have. So actually, what do we need? Just think about it. If we had to do this ourselves by our mind and not by a computer or by any hardware, would we do it ourselves? Well, actually, what we do in this example that I just showed you here above is that we have to remember what the last bit of information was. So this we can then use as the state. And the state can be that the last bit was 0 or the last bit was 1. There are no other states possible. So let's draw them. I draw here a circle and I call this the state 0, and I draw here a circle and I call this the state 1. And this is called the last bit state. Then what we have to do for all the inputs possible, how each state goes to what other state if possible. So let's look at this, what we were doing here. Imagine that we're in the state 0, so the last bit was 0, so for instance this one here, and we receive a 0. What do we get? Well, our state stays 0. We just have to remember the last bit that now stays 0. So input is 0. What if we're in the last bit was 0? No, first I have to say like this. So what do we have to output in this case? Well, if the bit stayed the same, then our output should be 0. Now I have to be careful with distinguishing between the O and the 0. So I will draw this convention, put a line through it. So if the state is 0 and we get an input of 0, our state stays 0 and we have to output 0. That's okay. So if the input is 0, and now we receive a 1. Actually, we have to remember this bit that now becomes 1. Input is 1. And the output, actually, we also have to output 1, because that is what we said. If it changes, yes, it changed from 0 to 1. Therefore, we have to output 1. Now, if we're in the state 1 and we receive a 0, what do we have to do? Well, that is a different state, different bit. So we have to say if the state was 0 and the input is 0, then we have to go to the state 0 and we have the output. Now it changed, so we have to put output 1. And finally, if the state is 1 and we receive a 1, we have to keep the state into 1 I equals 1, and the output should be 0, because 0 means that the state didn't change, that the bit didn't change. So now we have here what is called the, let me write it here, state diagram. And on basis of this, we can now start designing our hardware. So let's see how we do this. First of all, what kind of hardware are we going to select? We have these options, let's say. We can use JK flip-flops, we can call set reset flip-flops, T flip-flops, or D flip-flops. And now look for the state. We have to store this state. What are we going to use for this state? Now let's take a look. If the input is 0, our state will be 0. Look here. If the input is 0, for instance this one here, I don't know if you see it, this one here, if the input is 0, we go to the state 0. It doesn't matter what the state before was, if the input is 0, we go to state 0. And if the input is 1, for instance here or here, we go to state 1. Well, that seems to me very DT-ish, D-type flip-flop. It doesn't mean that you cannot do it with the other ones. It just means that this is probably the best solution. If you want, you can do this with the other flip-flops. It's more complicated, of course. But this one seems to me, the D-type flip-flop, seems to me to be the most logic solution. So let's then take this hardware. You remember this flip-flops. I will now delete this one here. So we take a D-type flip-flop for the state. This is going to be the state flip-flop state. So we take a D-type flip-flop. It has this truth table. If the D is 0, and we receive the clock pulse, of course, don't forget it, the rising edge, for instance, the rising edge clock pulse, and the D is input, is 0, the Q, the state of this flip-flop, will be 0. And if the D input is 1 plus the clock, then the output will be 1. So that is called the truth table. And then the excitation table, if we want to change the output, that is to say, if we want to keep the output 0, from 0 to 0, what do we have to put at the D input? 0. If you want to change from 0 to 1, we have to put a 1 at the input. If you want to change from 1 to 0, we have to put a 0 at the input. And if we want to keep the 1, we have to put a 1 at the input. That is just based on here on the truth table. We can we can draw the excitation table. So now let's see actually what we want to do. Let me put this down here. I want to know where is my state diagram. That was here. I no longer need the rest of this, so I can put this on top of it. What do we want? Let me put all possible combinations that are drawn here. We can have if the state and the input, I will draw it here, state and the input. If the state is 0 and the input is 0, well, let's take a look here. The state is 0 and the input is 0. Put here the previous state. Now the next state, and now it has to be, this time I will really say next state, and here previous state, and here input. So if the previous state is 0 and the input is 0, our next state has to be 0. And if our state is 0 and the input is 1, the state is 0 and the input is 1, we have to change the state, the new state, the next state has to be 1. If the state is 1 and the input is 0, if the state is 1 and the input is 0, we have to change the state to 0. And finally, if the state is 1 and the input is 1, if the state is 1 and the input is 1, that was this one, then our state has to stay 1. Now I'll draw here another column in this one. So actually, what do we have to do? From Qn to Qn plus 1, from the actual state or the previous state to the next state. Okay, so in this line it's from 0 goes to 0, from 0 to 0. And how to do this? How to do this? Well, look at this table. From 0 to 0, from 0 to 0, that is here, we have to input a 0 to the D flip-flop. Here, we are in the state 0, we input a 1, we want the next state to be 1, so we want to change the state from 0 to 1. How to do this? From 0 to 1, we apply a 1 to the input of the flip-flop. If the state is 1 and we get an input of 0, we want the new state to be 0. So from 1 to 0. How do we do this? From 1 to 0, that's a 0. And finally, if the state is 1 and we input a 1, we get an input of 1, we want the new state to be 1, so that is maintaining the state 1 now is going to be 1. So that is then also done, as you can see here, is done by a 1. So now we have here this column here is a logic function of these two inputs. How do we do this? Well, min terms, sum of products, product of sum, whatever you want to do it. Let me directly put here the Carnot map, which by now you should be familiar with. And actually, I think you can already see what the result will be. But never mind, let me do it. So we have here Qn, not Qn, I, not I, and this 0 that is here appears here, this 1 appears here, I don't know if you see this, this 0 appears here, and this 1 will go here, and now we have here these two ones. We can see that actually we were calculating for the D input, so D actually equals I, as you can see for this. Very nice. So actually what circuit, you can barely call it a circuit, but what circuit do we have? Finally, we have here our D-type flip-flop, D input, and we simply have directly the input, the D is equal to the input. So this is our circuit between quotation marks, because it's not really a circuit, is it? But this is our state. But this is not the output. Note very carefully, well, let me show it again once again here, that the output is not always the state. For instance, here it is. The output was 0 and the state is 0. But if we had here the input was 0, let me see here, the input was 1, the output is 1, and the state is 0. So the output is a different logic function of these two parameters, of Qn and I. And for that, I have to make a different circuit. So the output, because it's different from the state, that is a novelty in this circuit, is no longer, we can just copy the state to the output. So we need to design a new one for the output. Okay, well, that's not so difficult either. We have here Qn, I, and we put here output. There is no next state or whatever. This is simply a logic array. If the state is 0 and the input is 0, let me take a look here. Let me make this a little bit smaller. If the state is 0, we're in this circle here, and the input is 0, that was this, the output is 0, as written here. I have to put, all these things are 0. I'm not going to put these lines things. If the state is 0 and the input is 1, that is this one, the output is 1. If the state is 1 and the input is 0, state is 1, input is 0, the output, let me see, if the state is 1 and the input is 0, state is 1 and the input is 0, the output is 1. And if the state is 1, we are here, and the input is 1, then the output is 0. So that is a very simple logic array. Let me again put here the Carnot map, a little bit faster, Qn, Qn, not Qn, I, not I, this 0 here goes here, this 1 goes here, this 1 goes here, and this 0 goes here, and we see that the output, and we do this for the output actually is Qn exclusive or I. That is the function. So I can could also draw this circuit. However, there is a small problem. Namely, let me then put here the circuit that I was proposing. We would take this, the state is changing like this. This was my first half of the circuit, and now we have here that the output is exclusive OR of the input and the QN state. However, I hope that if you think a little bit about this, that this will go wrong, for the simple reason that actually what I want to do, let me see again if I can put here my output what I want. I don't want to sit now in front of it. I want that for my logic array output that it uses QN. Let me put this red. I want to use the previous state, QN, and not the new state. So what happens? Now, if you get, for instance, you get here a new 1, whatever. Let me also put this one red. Imagine you get here a new 1. I want to erase this one. Imagine you get here a 1. On basis of this new 1, it will do a calculation, and this one will actually go to Qn plus 1. This one changes. So if I do this kind of output for this circuit, in the beginning it will still use this input that is received and the old Qn, but the moment this one, this flip-flop here of the state has finished calculating the new state, then this new state will be used in the output for the output calculations. So instead of this, it will use actually Qn plus 1 instead of Qn. So that's not what I want. So Houston, we have a problem. But now let's then draw the final solution, because in the previous lecture I've shown you, or in some earlier lecture I've shown you the master reset flip-flop. So what we can do, actually I've made it here a nice drawing of that. We can actually use master reset flip-flops. So what we do here, we put here a master slave D-type flip-flop. So that is D, Q, not Q, and the output of this one then goes into, we can do it actually both ways, but we can put this exclusive OR with the input. So this one goes here, and this one then goes to another master slave D-type flip-flop, and we get here out. As you can see now I'll put black. Where do I have black? Here's black. So the moment here, for instance, you receive a 1, this one will start calculating and produces a new Qn plus 1. However, this one calculates, and it will only be ready not in the beginning. It's doing the calculation it's doing here, but it will only be ready at the output at the negative. Here, start calculate, and then it's ready. Only at the negative flank of the pulse, clock pulse, will it be put on the output. So this one is doing the calculation on the same clock, will start doing the calculation with Qn. And here Qn plus 1 is ready. So now this one, the second flip-flop, can do the calculation with Qn, and the first flip-flop will only output a new Qn when this one is actually already finished calculating and already has put the output based on Qn and not on Qn plus 1. Just take again a look, just listen again at the last part, because that is a little bit the most complicated. For the rest, I think this is quite easy how to build an edge detector, or in general how to build a finite state machine. Start with drawing all the states, then draw arrows how all the states are connected by the input, then start doing your logic array things and choose your flip-flop types, etc., and make your circuit, and then let's see at the end, you see if everything works according to plan, and then you are all done. I hope you enjoyed this lecture. See you in the next one.